Hello and welcome to IB Physics Help video podcast. This time coming to you from the Polish town of Sandomierz. Today's topic is electromagnetic induction. Many portable devices like torches, radios, mobile phones, e-readers or laptop computers use batteries as their source of energy. However, most of the electric energy we use comes from power stations. The production and distribution of electric energy rely on the principle of electromagnetic induction. So what is electromagnetic induction? In order to put the answer in context, let's discuss first the magnetic effect of an electric current. For a long time, electricity and magnetism were regarded as two distinct topics in physics. In 1820, the Danish scientist Hans Christian Ørsted discovered that a compass needle is deflected when an electric current flows nearby. At that point, the attraction or repulsion between two magnets was a well-established fact. What Ørsted discovered is that the effect of a current-carrying conductor on a magnetic compass is similar to the one of a permanent magnet. We can conclude that any conductor through which an electric current has been established creates a magnetic field in the surrounding area. We call this the magnetic effect of an electric current. There are many practical applications of this discovery. Electric motors are one example. We can increase the strength of the interaction between the circuit and the magnetic compass by using a coil or a solenoid instead of a straight wire. It is also worth mentioning that the strength of the magnetic field produced by a coil or a solenoid can be significantly increased when an iron core is added. This setup is often referred to as an electromagnet. The strength of the magnetic field produced by an electromagnet depends on the magnitude of the electric current flowing through it. The higher the current, the stronger the field. The direction of the magnetic field created by an electromagnet can be easily changed by simply changing the direction of the current that flows through the coil. Ørsted's discovery shows that electricity can be used to create magnetism. The next logical step is to investigate whether magnetism can be used to produce electricity. There are a couple of obvious ways of trying to produce electricity using a magnetic field. First, we can place a strong magnet into a coil and try to see if an electric current is generated in the circuit of the coil. The ammeter does not show any current. The second obvious attempt would be to set up two electric circuits, run a current through one of them, and hope that the current appears in the second one. To ensure that the two circuits are as close as possible to each other, I'm going to put the electromagnet inside the large solenoid. The ammeter does not show any current. So time to pack up, go home and try another day. But wait, the ammeter indicates a current when the electromagnet is switched off. Even more, the ammeter also indicates a current when the electromagnet is switched on. The only difference is that the current flows now in an opposite direction. Let's now go back to our first setup. The ammeter indicates the presence of an induced current when the magnet is removed from the coil. Furthermore, a current is also induced when the magnet is brought back inside the coil. The only difference, again, is the direction of the current. The two experiments demonstrate that magnetic fields could produce electric currents. This is called electromagnetic induction. The phenomenon of electromagnetic induction was discovered by the English scientist Michael Faraday in 1831. His key insight was to notice that a changing magnetic field can induce an electric current into a coil. Let's get back to the two experiments. In the first one, the strength of the magnetic field at the location of the coil decreases as the magnet is moved away and increases as the magnet is moved back into the coil. There is no induced current when the magnet is resting inside or outside the coil. In the second experiment, when the electromagnet is switched on or off, the current through it changes briefly, from 0 to a steady value when switched on, and from that value back to 0 when it is switched off. Consequently, the magnetic field of the electromagnet is changing. When a steady current flows through the electromagnet, its magnetic field remains constant. In what follows, I use the term induced EMF or induced electromotive force to refer to any influence that causes electric charges to circulate in a loop of wire as a result of electromagnetic induction. Induced EMF is measured in volts. The electric current that flows as a result of an induced EMF is called induced current, and it is measured in amps. A more systematic approach to electromagnetic induction requires the introduction of a new physical quantity, the magnetic flux. Consider a uniform magnetic field passing through a surface as shown on the screen. Let's assume that the area of the surface is capital A and the magnetic field makes an angle theta with a line perpendicular to the surface. The magnetic flux through the surface is defined as the product between the area of the surface, capital A, and the magnitude of the component of the magnetic field that is perpendicular to the surface. Phi equals B normal multiplied by A. Or another way of writing it is phi equals B times A times cosine theta, where A is the area of the surface measured in meters squared, B is the magnetic field strength measured in Tesla, and theta is the angle between the magnetic field and the normal line to the surface. The unit of magnetic flux is Weber. When dealing with a coil with n turns, the product between n and the magnetic flux through one loop is called magnetic flux linkage. Experimentally, it has been found that any change of the magnetic flux with time gives rise to an induced EMF. In the following demonstrations, I am using a set of strong neodymium magnets. The definition of magnetic flux suggests that there are three ways of producing an induced EMF. 1. By varying the magnitude of B with time. 2. By varying the size of the area A with time. Or 3. By varying the angle theta in time. Experimentally, it has been found that the induced EMF depends on the rate of change of magnetic flux through a coil. The induced EMF in a loop of wire equals the negative of the time rate of change of magnetic flux through the loop. EMF equals minus delta phi over delta t. This is Faraday's law of electromagnetic induction. In other words, if during a time interval delta t, the magnetic flux is changing by an amount delta phi, the magnitude of the induced EMF is given by the ratio delta phi over delta t. For those of you familiar with calculus, here is Faraday's law written using the time derivative. EMF equals minus d phi dt. The Greek letter epsilon is often used to denote the induced EMF. For a coil consisting of capital N turns, the total induced EMF would be n times as large. EMF equals minus n delta phi over delta t. Faraday's law formula gives us the magnitude of the induced EMF. For mathematical consistency, a minus sign is also present. It refers to the direction or the polarity of the induced EMF. In practical situations, the direction of the induced current can be determined by using the so-called Lenz's rule or Lenz's law. Lenz's law states that the direction of any electromagnetic induction effect is such as to oppose the cause of the effect. In other words, the induced EMF resulting from a changing magnetic flux has a polarity that leads to an induced current whose direction is such that its magnetic field opposes the original flux change. Note that Lenz's law is a physical fact and not simply an arbitrary convention about directions and signs. It is a manifestation of the tendency of systems to resist change, not unlike Newton's law of inertia. Furthermore, if Lenz's law were not true, we would end up violating the principle of conservation of energy. Let's apply Lenz's law in the case of one of the demonstrations shown earlier. When the magnet is moved towards the coil with its north pole nearer the coil, a current is induced in the coil and therefore a magnetic field is produced. What is the cause of this induced current? Obviously, the movement of the magnet. How can we oppose to that? By creating a magnetic field in the coil that is equivalent with the magnet with its north pole pointing towards the approaching magnet. Like poles repel. So the polarity of the magnetic field of the coil dictates in which direction the induced current flows. On the other hand, when the magnet is moved away from the coil, the direction of the induced current changes as it tries to oppose the moving magnet by creating a magnetic field with the south pole near the moving magnet, unlike poles attract. Here is another demonstration of Lenz's law. Eddy currents are induced in conductors when the conductor is moving in a magnetic field or when the conductor is in a changing magnetic field. They are called eddy currents because the electric charge moves in a swirling pattern. Lenz's law predicts that the electric charges move in such a way as to create a magnetic field opposing the change. This effect is sometimes called magnetic braking. In this demonstration, I'm using a copper tube and two plugs of similar masses and shapes. One is made of steel and the other is a neodymium magnet. When the two plugs are dropped through the copper tube, it takes the magnet much longer to fall through. Why is that? As the magnet falls through, different areas of the copper tube experience a changing magnetic field, and therefore eddy currents are induced. They have such a direction that their magnetic fields oppose to the cause of this effect, which is, in this case, the magnet falling through the tube. This produces a braking effect on the magnet. The braking effect is not observed in the case of the non-magnetic plug. Let's now recap the key points in today's podcast. In 1820, Ørsted discovered that an electric current flowing through a conductor creates a magnetic field in the surrounding space. The magnetic flux through a loop is defined as the area of the loop multiplied by the magnetic field strength multiplied by the cosine of the angle between the magnetic field vector and the line perpendicular to the plane of the loop. In the case of a coil with n turns, the flux linkage is defined as the number of turns multiplied by the magnetic flux through one loop of the coil. In 1831, Faraday discovers electromagnetic induction, the phenomenon of setting up an electric field by varying the magnetic flux with time. Faraday's law states that the induced EMF is equal to the negative of the time rate of change of the magnetic flux. EMF equals minus delta phi over delta t. Lenzs Law states that the effect of an induced EMF is such as to oppose the change in magnetic flux that causes the induced EMF.
That's all for today. Thanks for watching. See you next time.